Going to look at a particular type of rate of change question, that being exponential growth and decay. We're going to start with a very simple model using this idea that growth and decay is proportional to the population. A very simple idea, and when you think about it, it makes sense because the bigger your population, the more that are going to get born, the more that are going to die. The smaller the population, then the less, and so on. So it makes sense that growth and decay would be directly proportional to the size of the population itself. As a rate, I could write it like that. The P to T is equal to some constant times the population itself. Now, once we do some integration, we'll see how we can get this solution. But the solution to this differential equation is this. P is equal to AE to the KT. P represents the population at any particular point in time. A, when you think about it, has to be the initial population, because if you make T equals 0, you're going to get e to the power of 0, population equals A. K would be our growth, or if it was a negative number, it would be a decay constant, because if it was negative, it would be decreasing rather than increasing, and T, of course, represents time. So how do we prove it without integration? And what we'll see at this stage, if they want us to prove it, what they'll basically say is, well, show that this is a solution. So, all right, we'll prove that this is indeed a solution. And it's a very simple proof. All we have to do is differentiate our exponential there with respect to time, where we differentiate the power. Well, that's K, put that out the front. I get Ka e to the KT. Oh, what do you know? P is AE to the KT, so we get K times P. Very simple proof. Okay, well, let's look at this example then. We're told the growth rate, we've got some bacteria, is 10% of the population. And the initial population is, how many zeros have I got there? 1 million. Show that this is a solution. Okay, well, there's P. Differentiated, I get 0.1 AE to the 0.1 T. Oh, what do you know? That's 0.1 P. Yes, indeed. That is a solution to the differential equation. Well, let's now work out what the population will be after 3.5 hours. And I say, A turns out to be the initial amount. So there it is. A is 1 million. I now know my equation could be written this way. And there's my basic model. It really is just a substitution question. Sub in T equals 3.5, and we get our answer. And they wanted it to 4 significant figures. So we have 1,419,000 bacteria. Let's look at this one. Back in 1960, in a particular island, the population, so it's a small island, was 1,732. And obviously these people don't like each other, because in 1970 it's 1,260. Maybe they're killing each other because they want to take over control of the island. I don't know. Find the annual growth rate, which indeed would be actually a decay rate looking at these numbers, assuming it is proportional to population. So using our basic assumption. Well, if that's true, okay, the P to T can be written as constant times P. We know the solution to this will be AE to the KT. We just have to find out some variables here. Well, the initial population, 1,732. K is what we're trying to find. They've given me some information. 10 years later, it's 1,260. We have an exponential equation to solve. All right, let's make K the subject of this. I'm going to have to log both sides. There's the exact value, but they've said to the nearest percent. So there it is as a decimal. Now they've said find the growth rate, not the decay rate, so I will label it as a negative percentage. I suppose I could have said the decay rate is 3%, but either way, there's my answer. The growth rate is negative 3%. Well, how long is it going to take for this population to halve? Well, half of 1,732 is 866. Now you'll notice I've left K as K. I haven't bothered putting in that negative 3 for 2 reasons. Remember, negative 3% was an approximation. So I want to use the exact value, which I've got stored in my calculator. And I don't want to write down for K, what was it, 1 over something log. That's just messy. I'll just leave it as K. But there it is. T equals 1 on K log 1/2, which also happens to be, if you look at it, the half-life for radioactive material, where K is 0. Because you're doing exactly the same thing. You're finding how something decays. Okay, subbing in we get 21.786. So the question is, in how many years will the population be half of that? Okay, well, 22 years. This brings up an interesting point with these questions. Imagine I'd got the answer 21.3. Would you write down 21 years? Because are we rounding, or are we saying in how many years will the population be half? Well, if my answer is 21.3, then after 21 years it has not halved. So maybe I should write 22 for that as well. How do I solve that problem? I always make sure I write down my decimal approximation so they can see that, yeah, I did get the right answer, but I've gone this way and there's logic behind what I've done. Just a handful of those basic model questions to have a look at.